In this video, we're going to cover section 6.2, nucleophiles and electrophiles. And so when we discuss polar reactions in organic chem, they often involve these species. One species will be labeled the nucleophile, which is going to share electron density with the other species, the electrophile. So in ionic or polar reactions, these often involve charged species and bonding between nucleophiles and electrophiles. And so the question is, how do you identify a nucleophile or an electrophile? Well, from a very general perspective, a nucleophile is going to be a molecule that has electron density in which it can share. So it's going to be the electron donor, as we saw in previous sections, going back to acids and bases in chapter 3. We said that a Lewis base was an electron pair donor. Well, nucleophiles are very much like Lewis bases in the sense that they are the donors of electron density. Now, what's receiving that electron density in a reaction would be termed or called the electrophile. And so the electrophile will generally be a species that is somewhat electron deficient relative to the nucleophile. So it's always going to be a relative perspective in the sense that you're comparing two molecules and you're asking yourself which molecule is most likely to donate electron density and which of those two molecules is willing and most likely to accept electron density. Different pairs of molecules may change their identity with respect to nucleophile and electrophile, but you're always going to be comparing the relative ability of one molecule over another to donate electron density, and therefore the other would be the acceptor of that density. Now in this example here, what we're just showing is how, again, going back to section 2, how it's important, or pardon me, section 1, how important it is to recognize the differences in electronegativity between neighboring elements. And so we saw that if we had a chlorine atom directly attached to a carbon center, due to the fact that chlorine is more electronegative than carbon, then the electrons in that covalent bond are going to be unequally shared between those two atoms. They're going to spend more of their time around the chlorine atom. And so that gave rise to what we called a bond moment, a dipole moment. And overall, the molecule would have a molecular dipole, and that's shown by this particular arrow. And so this species, this carbon center within this molecule, we would call that carbon atom electron deficient. And so therefore, it could be, given the right nucleophile being present, the electrophile in an organic reaction, because it could accept electron density due to its partial positive nature. So in the other example of methyl lithium, we see that the complete opposite scenario, where now the dipole moment is directed towards the carbon center, which is going to leave a partial negative charge on carbon. And that's due to the fact that lithium has a much lower electronegativity than carbon. So in fact, the electron density that's in this carbon-lithium bond primarily resides on the carbon atom. And so we would refer to this carbon atom as being electron rich. So much so that we would typically draw this structure as really being an ionic structure in which there would be a lone pair on that carbon atom. And so we call this, in many sense, an ionic bond. But again, you'll see both descriptions used when it comes to lithium, organolithiums as they're referred to, or later on where we see magnesium forming interactions with carbon. Those are two scenarios where we have basically carbanions, and those are very nucleophilic and basic. So these provide some examples of nucleophiles and electrophiles. And again, when you're trying to understand which is which, you're looking for these particular aspects. You're looking for regions of low electron density and regions of high electron density. And so in these examples, this would be a potential electrophile, where this would be a potential nucleophile. So a nucleophile, that is a compound that contains an electron-rich atom that's capable of donating a pair of electrons. And so let's go over a few features of a general nucleophile. For one instance, for any given element, carbon, oxygen, nitrogen, primarily, negatively charged species are more nucleophilic than the equivalent neutral species. So if you have, say, a water molecule, H2O, where oxygen is neutral, versus the hydroxide ion, OH minus, where the oxygen has an additional electron and a formal charge of -1, the hydroxide is going to be more nucleophilic and basic than the neutral species. So the conjugate base in that example would be more basic than the original acid water. Now, for a given period of the periodic table or a row within the periodic table, the nucleophilicity and basicity is going to decrease on moving from left to right. And so as the electronegativity of an atomic center increases, its ability to donate electron density is going to go down. So we're going to see that the fluoride ion, for example, which we really don't discuss in much detail because it's very different than many of the other elements neighboring it, it holds on to its electron density so tightly that it rarely will be involved in any kind of basic or nucleophilic reaction. It's a very selfish atom in that sense. It's very electronegative. But when we compare carbon, carbanion versus a oxide, O minus, because of the lower electronegativity of carbon, it's going to act as a stronger nucleophile, or in many cases, a really strong base because it's willing to donate its electron density. So you can make comparisons within a particular row of the periodic table that's based on electronegativity. Now, for a given group that is a column on the periodic table, nucleophilicity is going to increase on moving from top to bottom. And the reason why we see an increase in nucleophilicity as we go down a column is somewhat due to the size of the atom as it increases. As the size of an atom increases, we said it's better able to, take on that additional electron density. But size also has another important effect or reason for improving nucleophilicity, and that's polarizability. So polarizability becomes an important feature for a nucleophile. And what do we mean by polarizability? Well, it's really the atom and the electron density around it is pliable. It's a larger region of space, and the electron density around those particular atomic centers is easily or more easily polarized. And so as a result, it can, in a sense, shape itself, or the electron density can be moved towards regions of electropositivity. So if you have a region that's partially positive, as you would encounter with a potential electrophile, if an incoming nucleophile is able to move its electron density around its atomic core towards that positive charge, that partial positive charge, then that is going to enhance its ability as a nucleophile. So polarizability becomes a really important feature as you move down the periodic table. And the most common example that we'll encounter is when we compare an oxygen center to a sulfur center. And we'll find that sulfur containing nucleophiles like SH minus, those are really good nucleophiles because of this polarizability effect, or the fact that they are more polarizable than a similar oxygen-centered species. So again, there are three main things that you can consider when judging the relative nucleophilicity as well as basicity, but we'll talk about the differences between that shortly. But for a nucleophile, the main characteristics are the neutral species will be less nucleophilic than a charged species. So a negatively charged species will be more nucleophilic. As you go across the periodic table, as you go across a row, as you increase electronegativity, the nucleophilicity will decrease. But as you go down a particular column or group within the periodic table, the nucleophilicity will be enhanced due to a polarizability. Now, I will note that with basicity, polarizability does not enhance the basicity of a particular species. So as you enhance the polarizability, or as the polarizability increases, as we go from, let's say, oxygen to sulfur, the hydrosulfide ion, SH minus, it is less basic than OH minus. So the hydrosulfide ion is a better nucleophile, but it's not a better base. Okay, so we want to keep that in mind when you're comparing the relative nucleophilicity of species as well as basicity. Now, what I've done in this next slide is I've tabulated using multiple sources. So I've gone through half a dozen organic chemistry textbooks and other reference sources that I use to somewhat categorize the relative strength of nucleophiles and bases. Now, in no means am I expecting any of you to memorize this table. This is a guide and a reference, and it will be helpful when you're working on assignment questions and preparing for examinations. And you'll understand these trends the more that you use them as we apply them in various reactions. But I want to highlight a few things about nucleophiles and bases from this table. And so you can see here when we talk about our relative nucleophiles, again, the negatively charged species, you can see that the first two entries in this table, these are all negatively charged species. These are better nucleophiles than the neutral species, which are found in the entries below. So that's the first point in our previous slide, is that a negatively charged species molecule is going to be, in general, a better nucleophile than its neutral counterpart. Now, the other feature that is highlighted quite clearly in this first entry is that larger atomic centers like sulfur and iodine, these being more polarizable, are better nucleophiles. And so that was the last point that we made on the previous slide. So you can see that these are your best nucleophiles if you're looking for a nucleophile for an organic reaction. Below that, in the second entry, you can see that we're now back to that second row, primarily, bromide being the exception, but we have our carbon and nitrogen and oxygen centered anions, and these species are good nucleophiles, but they're also good bases, as we'll see in the slide below. But the bromide stands out as being one of the better nucleophiles associated with this group, but not a good base, okay? But because of its size, its polarizability, it's one of the better nucleophiles as well. As you start to get into the neutral species, these are okay. They will act as nucleophiles, but potentially compared to the use of other nucleophiles, the reaction rates, the kinetics will be slower. And then you can see that water and the alcohols and carboxylic acids, these are very weak nucleophiles. And so your more stable species are going to be very weak with respect to their nucleophilicity. Now, shown below are the relative strength of various bases. And one thing to point out is that our strongest bases generally come from our second row elements. So these are the anions of carbon, nitrogen, and oxygen-centered species. So your carbanions, oxides, your amide ions, and so forth, your hydride also. These are very good bases, but not necessarily the best nucleophiles. You'll see that these strong bases are considered good nucleophiles, as shown in the second row, but they're not our best nucleophiles. So these species can act as both bases and nucleophiles depending on what they're reacting with, depending on the nature of the electrophile. If the electrophile is for example, a carbocation, then they're going to act as a good nucleophile. Whereas if your electrophile is a carboxylic acid, there's a good chance that there'll be a proton transfer, so it'll be an acid-base type reaction. In the second entry, the weaker bases, you can see that these are those sulfur-centered anions. So the polarizability has a reverse effect on basicity. So although these species are some of our best and excellent nucleophiles, they are considered weak bases for almost the same reason. That polarizability doesn't help with the ability of these species to act as bases. When we think of bases, we think of, high electron density. We want that electron density to be somewhat localized. If it's delocalized, then its ability to share electron density will go down. So polarizability, in a sense, is like the localization of that. It spreads out the charge, but with polarizability, it spreads out the charge just around a central atom. We also see that the neutral species, these are also weak bases. So again, those species are not going to be highly basic in character. They may have some nucleophilicity, but again, we also saw that those are relatively weak, especially when we compare them to the anionic versions of them. So the conjugate bases of these acids are much better bases. And so that brings up another point I should mention, is that when we discussed the relative strengths of acids back in section 3, we said that we would look to the stability of the conjugate base to understand that. So if we had a very stable conjugate base, we said that that came from a strong acid. Well, you can use that same strategy to identify the strength of bases, that the strongest bases are going to come from our weakest acids. So if you have, let's say, a conjugate base in air quotes that is not very stable, it isn't stabilized by resonance. It's not on an electronegative atom. So if you have a very unstable conjugate base, that A, increases its basicity, and B, just to confirm that, that most likely is coming from a fairly weak acid. So that's a good identifying feature of the relative strength of bases. Look to the protonated version of that base and compare the acidities. And you can use pKa values to assist you in that. So the higher the pKa value, the least acidic that species will be, or the less acidic it will be. The conjugate base of those weak acids will be some of our strongest bases. And we know that from looking at our alkanes, that if an alkane loses a proton, we form these carbanions, and these are our strongest bases that we use in organic chem. So again, please use this table as a reference, as a guide, and look for these types of trends that we just discussed. So beyond these negatively charged species and these neutral species that have lone pairs associated with them, pi bonds can also function as nucleophiles. They're not super strong, but pi bonds do offer regions of high electron density that can be donated if a good electrophile is present. And so we'll see this in later sections, specifically in section 8, when we start to look at addition reactions, that it's the pi bonds, and in section 9, when we look at alkynes, so alkenes and alkynes, these pi bonds associated with these double and triple bonds, these can act as electron sources. so electron donors. And so these can be also nucleophilic in character. Now, in terms of electrophiles, as we've said in the previous few slides, or in our opener, that these are compounds that contain electron deficient atoms. And so they're able and willing, they're capable of accepting that electron density, a pair of electrons. And so these can be regions of low electron density, as shown by these partial positive charges when we're assigning these delta positives and delta minuses to particular polar bonds within molecules, or these can be species that have formal charges of +1. And so carbocations are some of our best electrophiles because they are carbon species, carbon atoms that are electron deficient. They have one less electron than they normally should have in a neutral state. And so they're very willing to accept electron pair in the formation of a new covalent bond. So when we look at the carbocation species in more detail, we should recall that carbocations contain an empty p orbital, that carbocations are sp2 hybridized, which implies that there is an empty p orbital associated with it. So you may recall that when we look at our electron configuration for carbon, we have our 1s filled, our 2s, we have promotion. If all the 4 valence electrons were present, we would fill that last p orbital with a single electron. But that's not the case for a carbocation. A carbocation is electron deficient. So there are only 3 valence electrons around carbon. So when you're hybridizing a carbon center that only has 3 valence electrons, the result is 3 sp2 hybridized orbitals. And those sp2 hybridized orbitals are the orbitals that form covalent bonds with neighboring elements. But what's left behind is a empty p orbital, and that's what's shown in this diagram. You can't hybridize orbitals that don't contain electrons. We're only ever going to hybridize orbitals that contain electrons. And so in this example, because there are no electron density in one of those 3 p orbitals at the 2p level, we're going to have an empty p orbital. And so as a result, electron density is going to be easily accepted by that empty orbital from some nucleophilic species. Okay? And this is the same scenario for boranes. So BH3, boron only has 3 valence electrons, and so it's always sp2 hybridized when it has 3 valence electrons. Boron also has an empty p orbital. So we'll see that boron-containing compounds are also great electrophiles due to the fact that they have that empty p orbital willing to accept electron density from a nucleophile. So in summary, some common features of nucleophilic and electrophilic centers are summarized in table 6.3. And so you can see that inductive effects can play a significant role in whether a species is considered a nucleophile or electrophile. And again, we're going to use this strategy when looking at organic reactions. We're going to be comparing these features in a set, a pair of molecules. So we have to decide when you have 2 molecules reacting, which of those 2 molecules is most likely acting as the nucleophile and which molecule is acting as the electrophile. It's very important because the nucleophile will be sharing its electron density with the electrophile. And as we've seen previously, we'll use our curved error formalism to show that and for us to predict the outcome of that reaction. So inductive effects can help identify regions of high electron density and regions of low electron density. So in regions of high electron density, these are going to be your nucleophilic centers. In regions of low electron density, these are going to be your electrophilic centers. Lone pairs, species that contain lone pairs, these are going to be potential sources of electron density for these nucleophilic species. So nucleophiles that contain lone pairs are generally either neutral or negatively charged, negatively charged species being more nucleophilic, as we've seen or talked about previously. And so the hydroxide, for example, OH minus, it's going to be more nucleophilic than this neutral water species, but again, it's the lone pairs around that oxygen center in both species that is being the nucleophilic and the source of electrons. Species that are electron deficient, such as carbocations, carbon centers that are deficient by a single electron, these are very much electrophilic and willing to accept electron pairs from nucleophiles. And so, you see a carbocation almost 100% of the time, that's going to be your electrophile. And lastly, we saw that species that contain pi bonds, so these can be alkenes and alkynes, these pi bonds can act as donors of electron densities, and so they can be both nucleophiles and bases, so long as you have a very good electrophile present. And so we'll see that when we look at addition reactions in section 8 and section 9. So if you have any questions about nucleophiles and electrophiles, or if you have any questions about acidity and basicity primarily in this section, by all means, send me an email. We can set up a Zoom appointment very easily, or ask a general question in our forum and I'll respond. So thank you for your time, and we'll see you in the next video.